Welcome, everyone. We really are about to get started. Thank you, everyone, for coming. My name is Bonnie Cook, and I teach in the English department, and it's my pleasure to welcome you to today's presentation by Voices, a library lecture series. Voices presents speakers on timely and enduring topics each semester to broaden and enrich the scope of studies at Hudson Valley Community College. We have on the table, if you didn't see them when you come in, these yellow surveys. If you would pick these up and fill them out, it helps us to inform our future presentation. There's also a little barcode you can enter your comments online. That would be a great help for us. Put down what you like and what you don't like. Before I introduce our distinguished speaker, we would like to acknowledge we are gathered here on the sacred homelands of the Mohicaniac, or Mohican peoples, who are stewards of this land. Today, the community resides in Wisconsin and is known as the Stockbridge-Munsee Mohican Nation. We pay honor and respect to them and to their ancestors. Our speaker today, Bob Berman, is the world's most widely read astronomer. Since the mid-1990s, his celebrated Strange Universe feature has appeared monthly in Astronomy magazine. He is also the longtime editor of the Old Farmers Almanac, and he was Discover magazine's monthly columnist from 1989 to 2006. He has authored more than 1,000 published articles and been a guest on TV shows such as Today and Late Night with David Letterman. Bob Berman is the author of 12 popular science books, and listeners in 7 states can hear his Strange Universe program on WAMC public radio station on Sunday mornings. For 17 years, Bob Berman created and taught the summer astronomy program at Yellowstone Park for the National Park Service. He is the director of 2 Ulster County observatories and the Storm King Observatory at Cornwall, New York. He was an adjunct professor of astronomy and physics at New York's Marymount College. And this is the coolest part of all. Bob Berman also leads 3 annual expeditions to see celestial events such as auroras and total eclipses. So if you want to do something really, really far out and cool, you could, for example, go to the Arctic to look at the northern lights with Mr. Berman. It's my great pleasure and privilege to welcome Bob Berman. Thank you.
Thank you, Bonnie.
Thank you.
I appreciate that generous introduction, even if I did write it myself. But it's true about the coming on tours, because one of the aspects of astronomy that everybody loves is to have their minds stretched or blown and see spectacle. In fact, when we talk about astronomy, there's really 4 major areas that we might be talking about. There's the beauty, and that's what we were just mentioning. Probably the most beautiful of all. I mean, we could spend the whole program on celestial beauty, but let's spend a minute at least, because, hey, it deserves at least that. The most amazing has to be the total part of a total solar eclipse. In the 10 eclipses that I've led tours to see all around the world, I found most people weep from the impact of it. It's that beautiful. If you rate this 100 on a scale of what's the most impactful of the celestial spectacles, let's give that the 100 and then compare everything else to it. Not terribly far below it is the aurora borealis. If you get an all-sky display, and that's what we've been doing every year for the last 30 years in Alaska. You can get on board, find out the schedule, the costs, and the dates and stuff by going to, well, I guess the easiest is special interest tours, because they run these things. And then below that, you'd get a rich meteor shower. I know probably all of you have seen a beautiful shooting star at some time or another. Once every 20 or 25 years, we get a great comet. And in that case, great isn't just an adjective that means cool. Hey, look at that cool comet. No, great is actually the term for a comet that's bright enough to be seen from cities, where light pollution doesn't make it invisible. Comet that has a tail that sweeps across a big part of the sky. Once every 20 to 25 years, we get them. So they're not that common, but they are gorgeous. Many of these objects are gorgeous to the point of where you can't figure it out, where you've seen photos that were clearer, Hubble Space Telescope, now the James Webb Space Telescope. You've seen beautiful photos of Saturn, and yet a good backyard telescope, when you see it in person, people make sounds. They make almost animal sounds when they first see Saturn. There's something about the real thing. I don't know what it is, the vibe that it has. I'm from the Woodstock area, so that's how we talk down there. But there's something about seeing these things in person that are just absolutely amazing. So beauty is one major area of astronomy. Another is finding out what's what, research, which largely involves math and measurement and observations. And that's what's taught here and in all colleges, and that's what professional astronomers do. It's almost entirely math. So if you've ever thought about becoming a professional astronomer, just realize that that's what you're going to be doing, is math. A third area is, maybe we call it the classical part of astronomy, the part that's been mostly studied over the centuries. And that's the stars and the constellations. Not usually taught at colleges. But at any age, learning the bright stars and the star patterns, and maybe the lore and legend and mythology behind them that came to us from the ancient Arabs and the Greeks. And in fact, 2/3 of the stars have Arabic names, and the rest have Latin or Greek names. And the meanings, and seeing the patterns, and seeing what they used to be called, that's an area all by itself. Has nothing to do with research, has nothing to do with the beauty of it. So that's a whole separate area. And then there's a fourth, and that's what this rather short talk is going to be dedicated to. This is about figuring out what's going on with the universe. Probably every 7-year-old has wondered at some point or another, what is this place that I was born into? What's the nature of life and existence and the universe? And if you have any philosophical or metaphysical bone in your body, you've got to have wondered at one point or another, is the universe eternal? Was it born? Questions like that. And here is where there's been a lot of changes just in the last 25 years, and that's what this rather short talk, only half an hour, is focused on. This stuff that at one time was handled exclusively by the clergy, by religions, by philosophers, by metaphysicians. And nowadays it's cosmologists. The field is cosmology, which sounds like it's haircuts and perms and things like that. That's something else again. And this is where there's been huge changes that the public is generally unaware of, just in the last 20 years or so. So the question, what is the universe, sounds like a strange question. That's the title of this talk. But as we'll see, that gets to the heart of these old questions. The other areas too, the research areas, also have changed in the last century. Here's illustrated by how much astronomy has changed. Here's an old textbook from about 100 years ago. I mean, it's about the sun. What did we know about the sun back then? Here in chapter 1, all it just says is it's hot. The sun is hot. So you'd think that it would be in these areas of finding out the details of the parts of the universe, which is taught at the college level, that we'll be focusing on, but we won't be today. But when I emphasize our lack of knowledge, or the contradictions, the paradoxes, let's just be clear that I'm not putting down astronomy. The amount that we know and the amount that we've learned and are continually refining is spectacular. We know that the moon is 2,162 miles in diameter. We know that Mars' day, its period of rotation, is 24 hours, 37 minutes, and 23 seconds. And 100 years from now, when we keep observing Mars and refine that, that's not going to change by a minute. I mean, we have it down. So there's much that's sure in astronomy. There's much that's probably correct. And relatively little that's wrong on the fundamental level. So it's a little surprising that if the basics are so bewildering, and by basics I mean, what is the universe made of? Was it ever born? Will it die? What's the future? How do we relate to it? How does consciousness or awareness relate to the non-living, the living and the non-living? When we find that these things are still largely unknown, it just shows there's a split in astrophysics or astronomy, especially these days, between the stuff that we know and that we're sure about and that we study, and the underlying questions about it, about this universe. And universe is a good word because una means one. And we long ago discovered that the same properties prevail throughout the universe, the same fundamentals. The speed of light everywhere is 186,282.4 miles per second. And yes, I'm going to use English units like miles, because we do in Discover magazine and in astronomy and the Old Farmers Almanac, because the public is used to that. And of course, the world is using metric. Metric is not superior, but it does have the advantage of units being divisible by 10 or by multiples of 10, and that makes it much more logical to compare a gram and a kilogram, for example. But since the universe is being observed by us, people, it was not wrong to to have a measurement called a foot that was pretty much equal to the size of a man's foot. A yard being a step, a cup being equal to what a person could hold in their cupped hands. And we've made the universe pretty much follow in the units designed around ourselves. The metric system started out with a meter, that's the basic unit of length, and it was supposedly 1/10,000,000th of the distance between the equator and either pole. That's not terribly accurate. So as you know, the meter was for a long time defined by a platinum bar kept in Paris in a vault, exactly showing a certain length. There's no real logic to the meter. It's length, a little longer than a yard. I mean, especially when you consider that a foot just happens to be the distance light will travel in a billionth of a second. So there's actually some logic to the old antiquated English units. In any case, that's what I'll be using. And I think it makes more sense for most people. If I told you that rain generally falls at the rate of 8 meters per second, does that resonate with all of us here as much as if I told you that the average raindrop falls at 22 miles an hour? I said 22 miles an hour, that's the speed of falling rain. I mean, can't we grok that more easily than meters per second? I do. So that's what we use in the popular science magazines, and that's what I'll be using when we speak today. So we'll start off with probably the most basic question of whether the universe was born, and if so, how. We think of the beginnings of things as being natural because everything we know on Earth had a beginning. Every McDonald's Quarter Pounder had a moment of creation. Each bit of our furniture at home had a moment of birth. Things don't last forever. So it's natural to assume that the universe is the same and that we must have started at a certain point. And you've seen all the TV specials with people like Dr. Neil deGrasse Tyson explaining that everything began 13.8 billion years ago with a big bang. And then usually on the TV screen they'll illustrate that with just looks like bits of junk flying apart at huge speeds. Looks like an explosion in a macaroni factory. Not many people will look at the TV and say, wait a second, that's the answer to the universe, that we started out having popped into existence from nothingness. Is that really an explanation? I mean, what if some professor, and I used to teach college astrophysics, what if somebody assigned a group of researchers the job of figuring out the origin of something, and they came up with the answer that it popped out of nothingness? What grade would they get for that paper? Wouldn't they be told, wait a minute, nothing pops out of nothingness? It means you've missed something in your research. Not only did it pop out of nothingness, we're told, but it started out the size of a grape, weighing what the entire universe weighs, which, since I know you keep wondering about this, would be 10 followed by 50 zeros, tons. It's the weight of the universe. So a grape weighing that much popped out of nothingness one Saturday morning, 13.8 billion years ago, and first expanded much faster than the speed of light. I mean, almost infinitely faster than the speed of light, but it did this for less than a second. But ever since 1978, when Alan Guth of Princeton suggested this, it's been accepted because that's the only way we make sense of the universality of all the constants and the values of all the basic properties of the universe. I mentioned the speed of light, but everything else too. The most common element is hydrogen. I think most of you know that. But everywhere in the universe, most of the mass of hydrogen is in its single proton at the center, which weighs 1,836 times more than its single electron that goes around it. This is true everywhere. And when that single electron gets excited by nearby energy so that it jumps farther away from its nucleus, as it tumbles back to where it would prefer to be, it gives off a particular shade of red light, always red light, at 65, 63 angstroms. When I studied this stuff at school, we used angstroms. Actually, there was some tension because the physicists always used nanometers and the astronomers always used angstroms. Now we've lost the battle and everyone uses angstroms. So just move the decimal point over. It would be 656.3 nanometers. You don't care. But it's true everywhere. Everywhere you go in the universe, you get this exact same light when hydrogen is simulated. Now, why should that be? Why shouldn't the proton be a little heavier or lighter elsewhere? Why shouldn't the energy it gives off be a little different? Well, it has to do with the property of the electromagnetic force called alpha. Its value is exactly 1 over 137, fraction, 1 over 137. What do we do with that? It's one of the basic units of the universe. You try to derive it, you figure out how you get that, why it should be that and not something else. No one knows. This bothers astrophysicists. But it's true everywhere, and it's always been true. It also doesn't change over time. Back in the 1930s, almost a century ago, the great physicist Paul Dirac thought that light might get tired after it's traveled for billions of years. Could you blame it? And if it got tired, it would change its frequency or wavelength or color. But it doesn't, and these rules apply everywhere. So we really do live in a universe, and you don't get this evenness unless you had this expansion faster than the speed of light in the beginning. So there's a lot that we've learned about the universe as a whole. But on the other hand, there's basics that are now creeping into cosmologists' attention and emphasis. One of them is the role of consciousness or awareness. We're all observers of the universe. Does that matter? Generally, science would prefer it not to matter. We would like the universe to be the same and objects to be independent of us. So back 1 century ago in the 1920s, when the geniuses who created quantum mechanics, people like Max Planck and Werner Heisenberg and Edwin Schrödinger and all the rest, were studying this stuff and came up with, it's really brilliant because it explains how everything works on the smallest scale. And that brought up the question of whether the small scale and the larger scales all work together. It turns out they don't. We have not just science, but our minds work to make sense of this scale of, you might call the macrocosmic scale, the scale of things you can see and touch, looking for your socks, ordering that cheeseburger. And when we think about things, our minds, from the time we were little, developed and were trained to make sense of things on this scale. And we could call it symbolic knowledge or logic, and it works by symbols. The word water is not actual water, and it doesn't matter. If you say to somebody who's by the sink, hey, can you get me a glass of water? They know what you're talking about. It doesn't matter that you've used the word water. It works. And if a waiter brings you a sizzling hot dish and says, watch out, don't touch it, it's hot, that works. You know it's hot. You don't actually have to have the direct sensory knowledge by touching it yourself. But you should be aware that that changes things, because knowledge that's gained through symbols is limited. It's limited to previous experience. I don't have to tell you that a person who is born blind has no idea what the color blue would be like to experience. And there's no way you could explain it to them. And yet a glance at the sky, and there it is. The direct experience, it's self-evident. So there's a difference between knowledge that's dualistic, and we say dualistic, this is a word borrowed from the Buddhists and the Hindus, in that there's two things going on. There's the actual object, in that case I said water or salt, and then there's the symbol for it. And it's important not to imagine that they're the same. Unfortunately, too many do in the sciences, especially in astronomy, think that the symbol is the thing, and that we have actual knowledge where we don't. And that limits us in a bunch of ways. For example, there are things you cannot picture, just like that color blue to the person born blind. Like if we talk, which we will in a minute, about infinity, is the universe infinite? Now, no one can picture an infinite universe, even though in the last few years more evidence is accruing that the universe may indeed be infinite. Infinite in size, infinite in content or inventory. And so that would mean the galaxies just go on without end. Some of our parents may have told us that when we were kids, and they wanted to just stop our questions. And we said, hey, what is the universe? How big is it? They might have said, oh, it just goes on and on. Well, maybe they were right. Starting to look like they may have been right. But you can't picture that. I can't. You can't. Nobody could picture infinity, something going on and on without an end. Then on top of that, there are ways that we're trying to make sense of it. Some of them work, some of them don't. You've all heard of string theory. Now, back about 30 years, it looked like it might be a way of explaining the four forces. As we all know, there are only four fundamental forces in the universe. Maybe one quick way of explaining a force is something that will cause something to behave a certain way or change its path, change its movement without touching it. One force we encounter all the time is gravity. You jump up, nothing physically has to touch you, but you come down again. One of them is the electromagnetic force. That's responsible for things like magnetism and light and almost all of our technology. And then there are two forces whose reach is very, very, very small, that only work within atoms. One of them is called the large force, the strong force. One is the weak force, easy to remember. You've got to have these, otherwise you don't have the universe that we see. Because every atom except for hydrogen has to have more than one proton in its nucleus. And as soon as you have more than one touching each other, protons all have the same electrical charge of +1. Like charges repel each other, and they repel each other strongly. So if you have, let's say, oxygen with 8 protons, those 8 protons don't want to be next to each other and stay together. And so without the strong force, which overcomes the electromagnetic force within atoms and lets those 8 protons be together, we've got no oxygen. In fact, you've got no elements at all in the whole universe except for hydrogen, which would make for a pretty boring universe. So you hear the term strong force, you know it only acts within atoms, you might say, all right, so what? But you can see these are important. So there are only 4 forces, but when we are learning about them and trying to figure out how they arose, it looks like in the early seconds of the universe after the Big Bang, 3 of them were one entity, and only gravity didn't fit in. So we'd like to see how they arose, and string theory does that in a clever way. I mean, it's largely mathematical, but basically reality, if you could look at the tiniest level through a microscope stronger than any that we have or will ever have, you'd see that reality is built of wiggling lines or strings that connect with each other, and how they loop and connect or don't connect will determine what force you have, whether it's gravity or electromagnetism or the strong force, etc. The only problem is that it doesn't work in our universe. You have to have extra dimensions, at least 7 extra dimensions. Now, here we have 3 physical dimensions, length, width, and height, and then the 4th dimension of time. So string theory doesn't work in our reality. You have to have extra dimensions that no one can picture, that no experimental evidence can reveal, that there's no sign of, and predictions as to what this would mean have all fallen short. If there's string theory, what good is having a theory if you can't predict something with it that then proves to be true or not true? In other words, it has to be falsifiable. A theory is no good unless it can be falsifiable. You can find a way to find out if it's wrong. Because of my shows now on public radio for decades, got a lot of email from people who write all sorts of things. I mean, people are imaginative. A recent letter was, could the expanding universe be due to the universe expanding into the vacuum beyond it, and therefore that vacuum is sucking everything out? Could that be the cause of the expansion? And I try to answer everybody. I'll say that, first of all, to give this any thought at all, scientists would have to find a way to actually do an experiment or an observation to see if it's true. And there is no such thing. And secondly, that's not what really happens with the expanding universe. So you have to know enough basic physics to even get a handle on what's going on. But we brought up consciousness because those quantum mechanics guys, Max Planck and the rest, as brilliant as they were, started delving into what is the basics of this universe. I mean, what did nature build itself out of? You notice we'll neglect any possible religious explanation. That doesn't mean that God doesn't exist. It's just that that's no explanation. Generally puts things off a step. Like if somebody says, well, why not just say God created the universe? I would say, well, fine, but then what created God? I mean, you know, this kind of thing. You're not really answering anything. You're putting off solving the mystery by a step. And so we don't do that. So I'll use the word nature instead. So what is this? What is the basic nature of the universe? Is it energy? Is it matter? Is it that hydrogen atom? It turns out that the most common particle in the universe is something called a neutrino. There's over 1 million neutrinos for everything else combined. And then for every neutrino, there's about 1 billion photons. Photons are bits of light. And so these guys and astronomers since then have been trying to solve that. Now, does that mean I have 10 minutes left? Yes. And then we'll do questions and answers. Yeah. Okay. So let me just look at my notes and see if we could jump ahead quite a bit to what these guys figured out. They decided that the basics of the universe was actually consciousness, that is mind, that is awareness, perception. When we do an experiment or an observation, we can't do it unless we're conscious, right? And when they were looking to see what creates what, the one thing that they couldn't find anything that created it was consciousness. And they realized that from the time of our birth, all of us have been aware. We've had awareness. What is this awareness? Some would say, oh, it's something that starts with the brain. Brain creates awareness. But it doesn't. No one's ever been able to figure out a way that the mostly water, which is what the brain is made of, and salt and electricity going through neurons can create consciousness. No one's figured out a way to do that. The brain must have something to do with consciousness, because if you have an accident or drink too much alcohol, your consciousness will be affected. But that doesn't mean it creates it. So they saw nothing that was more fundamental than consciousness. Fundamental means it's not derivable, I guess is how you pronounce it, by anything else. It's always there. And that's strange because they saw consciousness as always existing. If that's true, it would mean that this universe, instead of defining it as its weight, as I did before, its the amount of energy, it could be defined as a self-aware entity, maybe an eternal self-aware entity. But the problems quickly grew worse than that. As we studied the universe, we found that the matter in it is only 5% of the weight of what's here. It's dwarfed by dark matter. You've all heard the term. Dark matter is something that has gravity. It'll pull on things. If there's dark matter in our solar system, planets will orbit the sun differently. We see galaxies, every galaxy, including our own, rotating differently. Rotating in a different way that would make sense when we survey what's in the galaxy, even adding unknown stuff like black holes. And so we see that there's about 7 times more dark matter than there is ordinary baryonic matter, made of the 92 natural elements. Dark matter, what is this? It's something with gravity, but yet there's nothing there. We've also found that the universe is even more made up of dark energy. Now, this is a repelling force that empty space is filled with. Empty space, isn't that just a vacuum? Well, we used to think so, but we now know that empty space seized with power. I mean, real power. Some people call it zero-point energy, Z-point energy, or vacuum energy. But we now know that the empty space between stars has so much power that a mayonnaise jar worth of it could boil away the Pacific Ocean in 1 second. And you still wouldn't use it up because adjacent dark energy would replace it quickly. So the dark energy in the universe is the major constituency of this universe. What's mostly here is dark energy. Einstein taught us that energy and matter have an equivalency. One can be converted to the other. We saw that for the first time, unfortunately, with the atomic bomb explosions during World War II, when a simple gram of uranium or plutonium could be converted into the same amount of energy that could light up a city for a week. So they convert one to the other. So if dark energy rules the universe, and it does, because the universe's expansion, which we always assumed was slowing down, it has to slow down because everything has gravity. So like a giant spring, all the expanding galaxy clusters are pulling on all the others, and they're going slower and slower. And back when I studied this stuff at school, what we were looking for was to figure out exactly how much it's slowing. We wanted to know the rate of expansion, which, although it's usually given in kilometers per second per megaparsec, which won't make any sense to anybody here, I'll make it simple. The rate of expansion, in case it comes up at a party, is that for every million light years further that you look, an object will be rushing away from you another mile per second faster. That's pretty easy. Will be rushing away from you 13 miles per second faster. 13 miles per second for every million light years. So if you're looking at something 100 million light years away, some galaxy clusters, the larger part of the Virgo galaxy cluster, that's 100 million light years. You just take 100 times 13, and you get 1,300 miles per second. Are they really rushing away from us at 1,300 miles per second? Meaning they could go from here to San Francisco in 3 seconds? Less than 3 seconds, yes. That's we call it the Hubble constant, the Hubble parameter. That's the expansion of the universe. Question is, how much is it slowing down? It's got to be slowing down because everything is pulling on everything else. But no, we learned only in 1998 that the expansion of the universe is speeding up. Now, how is that possible? Galaxies don't have rocket engines on them. How can this expanding universe be going faster and faster? And the answer, which is another one of those non-answers in this search for what is this universe, is that the space, the empty space between galaxy clusters, contains this repulsive anti-gravity thing. We don't know what it is. We call it dark energy. And that makes up most of the universe. So we're starting to see that it's getting harder and harder to figure this out. First of all, we have a small inventory of the universe. There's only 2 universes, and I know multiverses are popular these days. Why don't you put on the first picture just so that we can have a pretty picture?
We have about 3-4 minutes before Q&A.
Okay. This is what's going to happen next year. Just north of here. It's a total eclipse of the sun. Just in case I forgot to get to it later, since there is no later, you must get into the path of totality. The partial part of the eclipse, where you need eye protection, like a filter, or you need to project it onto a surface, is not particularly glorious. It's not particularly interesting. The total eclipse will make you weep with its power and its majesty. Somebody on one of our tours told me afterward, one of the eclipses, the one in 1980, she said she felt that it was the home of her soul that she had visited. But you've got to see it to understand it. Once you've seen it, you'll get it. They're rare. For any given spot on Earth, a total eclipse of the sun only happens once every 360 years. We last had one here back on January 24th, 1925. And if it's cloudy, you have to wait another 360 years. So you've got to travel for them almost always. So it's very rare that you're going to have one coming as close as Burlington, Vermont. Go online, click on Total Eclipse of 2024. It'll be on April 8th. There'll be a map showing the path of it, and put yourself in that path. You don't want to be near the edge because that'll shorten the eclipse. It's only 2 minutes of the total part. So you don't want to turn that into 20 seconds, let's say. So you want to be somewhere in the middle half of that long ribbon. And it's close enough to drive. You're not going to have another one in your lifetime, well, near the end of the century, but that's a long time away. But the biggest thing that those guys learned was that everything that happens occurs within the mind. Like, you'll all assume that I'm far outside your body. The stages, those flags are, we're nowhere near your body. But people from Isaac Newton onward, many physicists have realized that light, which is how we learn almost everything as human beings, has no brightness or color. Light is actually a pulse of magnetism, and at right angles to it, pulses of electricity. That's why we call it an electromagnetic phenomenon. Electromagnetic energy. You can't see electricity and you can't see magnetism. So the universe actually has no brightness or color. The sun is not actually bright out there. A sunset is not actually red. What happens is that energy, once it gets into our brains, particularly in the occipital lobe, our brains do something with it and create everything that you see. What I'm saying is that everything you see is occurring in your mind, not in the external world. We've been taught, and our language emphasizes that all of the stages in front of your nose somewhere. But you're actually, and that your brain is just this mushy, dark place that you can't really access in terms of experiencing it. In truth, you are accessing your brain's interior with every glance at anything all your life. And there are tricks with that too, like yellow probably doesn't exist in real life. Let me give you a quick demonstration. Yellow is really just when red and green light hits you equally. Here's red light, here's green light. Let's see if we reflect both of those colors back to you. You'll see yellow. You see yellow where the two are meeting? Well, even though nobody is saying yes, I'll say yes for you. So it turns out that consciousness or awareness is crucial. And there are experiments like the double slit. You have to look it up yourself how it works, that show that knowledge in our minds changes nature. Whether an electron is a wave or a particle like a bullet depends on what you know, how you set the experiment up. And these guys realized this 100 years ago, that our awareness, our minds are central to the experience of the universe. This is about all the time I have before questions.
Yes, and this really, honestly, Bob, we need about 3 hours. This is, I mean, I don't know how you talk about the nature of the universe in 40 minutes, but we would really welcome some questions. So raise your hand and don't be afraid. No questions too silly here.
Yes, no questions. We used to like to say on the radio, there's no such thing as a stupid question, until I realized that that was a lie. I've stopped saying that. For the eclipse in the Albany area of May 10th, 1994, we had a partial eclipse. I warned people, listeners, not to look at it with the naked eye because they could damage their eyes. One caller phoned the station. Marcy was there. Here's my witness. And this caller said, if the eclipse is so dangerous, why are they having it? So it's not really that there's no, don't be afraid to ask questions because there's no stupid questions.
Here in the back. Let's start with you, sir. Nice and loud.
Would the universe exist to someone that can't experience it? For example, if a guy doesn't have eyesight, would it exist?
Can you repeat the question, Bob?
Yes, does the universe exist for someone who can't experience it? Most physicists today would say no. And I can quote, this is going to sound wild, but probably the most prestigious physicist in Britain, Martin Rees, cosmologist, here's a quote from him. He said, the universe could only come into existence if someone observed it. This really answers your question. It does not matter that the observers turned up several billion years later. The universe exists because we are aware of it. Now this sounds outrageous, but it can be proven. Look up double slit experiment and you'll take the first steps towards seeing how it works.
Other questions? Here's one right here.
Yes?
Is the universe expanding faster than the speed of light?
Yes.
How can that be if the speed of light is fast?
The speed of light is the fastest that anything can go if it starts off slower than the speed of light and has to be propelled because it would take infinite energy to go faster than the speed of light, and that infinite energy doesn't exist. But in this case, at a distance of 13.8 billion light years from us, everything that's expanding away from us is going faster than the speed of light because it's not moving. Rather, the empty space, remember I said space has this anti-gravity property. Dark energy is what's inflating, and the space itself is getting larger so that anything in it is being pushed away. So it doesn't have to propel its mass away from us. The empty space is inflating, and that's the escape clause on that one. Yes.
Got one here and two over here, Bob.
Yes, sir?
So, if one wanted to view the solar eclipse that you said will be happening in 2024, what is the safe way to do that so you don't go?
Safest way to view the eclipse on April 8th, 2024 is first to get a filter for the 1 hour partial phase so that your eyes are safe. And the safest is a shade 13 or 14 welder's goggle. Go to any welding supply store. They're usually in the most rundown part of town behind fences with snarling dogs. You go in there and it'll take them a week or two to get it but you have to make sure you get a 13 or 14 shade. The normal welding filter will still hurt your eyes because welders generally use something like a 10. You want a 13 or a 14. I prefer 13s. And they get a few of them. They're only a couple of bucks each. And then you can use that for the hour-long partial eclipse. Then comes totality. And when it's total, the filter can come down and you can look at the sun safely. You can even use binoculars or a telescope and still view the eclipse safely when it's total. So make sure you get yourself into that path of totality. For example, all of Burlington will be across the Lake Champlain in Plattsburgh will also be in totality. You'll see also Rochester and Buffalo and many other places. Yes? I didn't hear that. Would you repeat that loudly to me?
Can't hear the question.
If the expansion of the universe were ever to slow down, would we be able to figure out when it would stop expanding?
If the universe ever slows down, which we thought it would do as recently as the 1990s, and if it ever slows down, could it come back together again into one, like another Big Bang? Is that your question? Oh, stop. Well, that was the thinking back then. There's one model for the universe that was called the oscillating universe, that the universe expands and then contracts and then maybe has another Big Bang with new laws of physics, and that the universe breathes in and out like the old Hindu legend of the breaths of Brahma every maybe 20 billion years. New laws of physics, things that can't happen in our universe, things like gravity being repulsive, taxes going down, things that are impossible for us. And we used to think that that was very possible, but maybe likely. Now it doesn't seem so, although since we don't understand dark energy to begin with, we can't say for sure that it won't reverse itself in the distant future and the universe will then be dominated by gravity. Right now it's still dominated by gravity on the local area. In case you wondered why the solar system stays together and our galaxy stays together, it's because gravity rules on the small scale. The larger scale, clusters of galaxies are expanding away from other clusters of galaxies. So when we say expanding universe, that's only on the larger scales. On the local scale, like within our galaxy, there's no expansion.
Know they're conscious? Does a rock know it's a rock?
The thought is there is one consciousness, and that in the experience, you mentioned Buddhism earlier of samadhi or satori, or they have different names for it, cosmic consciousness, awakening awareness. One becomes unified with a single consciousness. So the mistake we make is what they call seeing things dualistically, that each human, each animal, or a rock are islands of separate consciousness. That's the way we all feel. Don't we feel like we are here behind our eyes and you're there and I can't wiggle your toes and you can't control my snoring, as Marcy will tell you. No one can. But in this other state, the blissful state or the truth state, you see there's a single consciousness that's in the universe. And then it changes. You wouldn't ask that question then. You'd maybe have other questions.